Good morning, class. Today's April the 20th. Is that right? Yeah. And I'm going to start a new chapter today. It's chapter 10. It's on gases. It's the last thing you have to know in your curriculum for grade 11 and for college grade 12. I've already uploaded chapter 10 notes. Let me know if you can read them and copy them. What I'm going to do is go through the notes and explain a few things, but I won't put up all the notes on the board. It's just not really practical to do that. So I don't know what the situation is with regard to your marks. I'm putting out a mark for April 23rd. Okay, I've marked your tests, the ones that you gave me through the internet. I'm almost done, so you'll be getting a mark for that too if you haven't already done so. And that doesn't mean, though, that you don't need to learn a few more things. So I'm going to keep on teaching because I'm still getting paid. So I don't feel it's right for me to just sit here and do nothing. You guys can benefit. I don't know if this is going to count. I definitely know it's going to be needed for when you go to university. I imagine the universities are going to have to implement some remedial programs. I'm sure they'll think of something. But it doesn't hurt for us to do what's already written down for us in the curriculum. This is what I would be teaching if we were in class right now, so take it or leave it. I'm going to offer it. So this is about gases. The atmosphere we breathe is a mixture of gases we call air. It is composed of 78% nitrogen, 21% oxygen, 0.9% argon, and 400 parts per million of carbon dioxide, which is way less than 1%. 1% would be 10,000 parts per million. So we have 400 parts per million carbon dioxide. Just an interesting observation, which could put things in perspective regarding global warming, so-called, is that in the history of the Earth, in the geological history of the Earth, there have been times when we have had more than 10 times that amount of carbon dioxide in the atmosphere. And, well, we're still here. We're here. Dinosaurs aren't. Maybe you could argue a case for saying, well, it got too warm for the dinosaurs. I don't think so. I don't think it got too warm for the dinosaurs. In fact, I think it got too cold, probably as a result of an asteroid that hit 65 million years ago, for which they have evidence of near the Yucatan Peninsula. So this large asteroid hit, caused a massive plume of ejecta, that some of which circled the Earth because it went into orbit. That's how hard the meteor hit. And it just plunged the Earth into a sort of nuclear winter for a period of weeks, months, we don't know. But that's what a lot of scientists say killed off the dinosaurs, because 65 million years ago, all of a sudden they disappeared. And then, life came back. It took a long time, but it came back. So the Earth's geological record contains evidence of pretty significant fluctuations in the content of both oxygen and carbon dioxide. If you go back 350 million years ago, you'll find that the oxygen concentration is believed to have been in the 30s, 35% oxygen. So insects were a lot bigger then. There were a lot of plants on the Earth producing oxygen. So the Earth was like a big rainforest, basically. And that was where all the deep layers of coal were deposited. It's called the Carboniferous period, because there was a huge amount of carbon deposited on the Earth's surface, carbon which we now mine in the form of coal. Apparently there were not as many fungi that can decompose wood or lignin or components of wood at that time, so the wood was able to persist long enough without decomposing, and it formed these very deep deposits. All very interesting stuff, but we're getting off topic. The atmosphere also contains traces of hydrogen, fluorine, chlorine, helium, neon, krypton, xenon, very small amounts. And of course, there are other things that we would call organic volatile solvents, many of which are probably potentially detrimental to health. I guess we could call them pollutants. I would also think that the concentrations of those potentially toxic, or I wouldn't say toxic, but maybe they have an effect on your health that would be less than optimal, even within our own homes, because we live inside these closed boxes with insulation to keep the cold out and the heat in and so on, and that tends to accumulate gases that outgas from the things that we use, from appliances, from devices that we make out of different plastics. So that could be a matter of concern for people who have a sensitivity to them. The interesting thing about gases is that they're compressible. You can't really compress liquids and solids, at least not with pressures that we're accustomed to dealing with, but you can compress gases, and that makes it possible for them to store energy, which is why a gas explosion has a danger of creating shrapnel, because when something fragments, say if a car tire explodes, pieces of rubber can go flying and hurt you. Well, car tires usually it's not a big deal, but truck tires, it is more dangerous because truck tires are usually inflated to higher pressures. Gases mix easily and completely. And also, the really cool thing about gases, at least that I think it's cool, is that the air we breathe only takes up about 0.1% of the total volume of the space it occupies. So we're basically standing almost in a vacuum, if you think of it. Well, we don't have a vacuum because the molecules are moving around. Air pressure is caused by the fact of air molecules transferring their momentum. Air molecules fly something like 400 meters per second at room temperature, and they're incredibly minuscule, but there's just so many of them that they exert a steady pressure on every object that they impinge upon. Why don't we feel that pressure? Well, because we have the same pressure acting on the inside. So our bodies are pressurized to the same extent inside as they are outside, so we don't feel the effects of air molecules. But if we were to suddenly increase our altitude or decrease our altitude, then you would feel it with the sensitive parts of your body, like your ear. Your eardrum is sealed partially, but there is a tube connecting your eardrum, your ear canal to your throat, the eustachian tube, I think it's called, and that can open up and release the differences in pressure. But if you go scuba diving, every time you go down a couple feet, you'll feel the pressure of the water on your ear. So what they say when they instruct you on how to go scuba diving is they block your nose and you gently blow, or you don't even have to really block your nose. Sometimes it's enough to just swallow some saliva, and the act of changing the geometry of your throat is enough to open the tube and equalize the pressure. If you have a cold, you don't want to go scuba diving though, because that tube tends to get clogged with mucus, and then you can't equalize the pressure, and you can get a painful situation where the air pressure won't equalize. What is pressure? Pressure is a derived unit. It's made up of two units: force over area. And force itself is also a derived unit, but it goes like this. Pressure is equal to the force exerted by something divided by the area over which it's exerted. In the case of SI units, force is measured in newtons, which has units of kilogram meters per second squared. The area is measured in meters squared, that is. And the pressure has units of Newton per meter squared, and we call that pascals. The SI unit for pressure is the atmosphere. Actually, don't quote me on that. It's either the atmosphere or the Pascal. Well, Pascal we know, but when they do calculations of gas pressure, they'll use kilopascals, they'll use pascals, sometimes they use atmosphere. So depending on which unit you use, and certain units are more convenient to use under certain circumstances. So we don't slavishly adhere to using only the SI unit because it would just add unneeded complication to certain types of calculations. So there are two units that get used a lot. That's the atmosphere and the kilopascal. You'll see later why. Another unit of measure that's often mentioned is the torr. The torr is named in honor of Evangelista Torricelli, the guy who invented the barometer. What is a barometer? It's basically a tube open on one end that they fill with mercury, and then they invert it into a dish of mercury. And what they found is when you do that, the mercury will fall to a height of about 76 centimeters if you're at the surface of the Earth, because the weight of the atmosphere is enough to lift a column of mercury that high, about that much. Okay? And if you used a different liquid that was less dense, it would be able to lift it higher because it would be less pressure exerted by the liquid. But mercury is the perfect liquid for making a barometer because it has a density of around 13.4. So it makes for a barometer that is manageably tall. It's not something, if it was made of water, you'd have to make it 32 feet tall. So Torricelli noticed that when he ascended a mountain with his barometer, that the barometer registered a lower pressure. And the higher he went in altitude, the lower the pressure registered by the barometer. So he realized that as he left more and more of the atmosphere below him, there was less and less pressure on the mercury in the dish that was pushing the mercury up into the tube. So he concluded that there is air pressure on the surface of the Earth. We don't feel it, but it's there. So a barometer is a glass tube filled with mercury, a high-density liquid inverted in a dish of liquid mercury. Atmospheric pressure holds the column of mercury up, raising it to a height of 76 centimeters or 760 millimeters of mercury. And that's a commonly used form of measurement. And also in honor of Torricelli, they call 1 millimeter of mercury the torr. 1 torr is equal to 1 millimeter of mercury. When you get your blood pressure taken, the two numbers that they read are the systolic pressure and the diastolic pressure. So when your heart pumps, normally the pressure will spike to about 120 torr, or millimeters of mercury. And in between contractions of your heart, the pressure will drop down to about 80 millimeters of mercury. If you're small of stature, if you're a woman or a child, pressure might be around 90 over 60. But it's in that neighborhood. And typically, if it goes higher than 120 over 80, it's a cause for some concern, especially if it gets into the area around 150 or 140 over 90, then that's considered high blood pressure, and it can start aging the components of your cardiovascular system and damaging your kidneys, so that it's a big deal. It's important to bring that blood pressure back to normal numbers. Anyway, let's look at some of the different units that are used for pressure. We have 1 atmosphere, which is the pressure of air at the bottom of the ocean of air that we call the atmosphere. We're standing at the bottom of an ocean of air. If you go up 100 miles in altitude, you'll be in what people would normally call space. I think when they put satellites in orbit, typically they'll put them at a height of either 100 or miles or 100 kilometers, I can't remember which, because it's by that altitude there's very few air molecules. It's not as though the atmosphere ends abruptly. It just gets thinner and thinner as you go up. But once you get to about 100 miles altitude, the number of air molecules that are there are so low that for all intents and purposes, you're almost in a perfect vacuum. So 1 atmosphere is equal to about 14.7 pounds per square inch. It also equals 760 torr. It equals 760 millimeters Hg. That equals 101.325 kilopascals, or 101,325 pascals. It also equals 1,013.25 millibar. I haven't heard that one used in a while. And it's about 29.92 inches of mercury. You'll see in some old-fashioned barometers, they talk about inches of mercury. The whole premise of the barometer is and they use it for predicting weather, is the moisture content of the air. If the air has a high moisture content, because water only has a molar mass of 18 grams per mole, and the average gas in the atmosphere has a molar mass of, say, like nitrogen, 28 grams per mole, when you have a lot of moisture in the air, it actually brings the average density of the air down, and it also tends to decrease the air pressure. So when you get a low pressure zone, it means there's a lot of moisture in the air that's coming. And typically that means clouds, rain, stormy weather. Also, if you have a cyclonic weather, if you have a hurricane where you have large amounts of air masses rotating, that tends to cause low pressure zones. So whenever you have a low pressure zone, when the barometer is dropping, that typically means you're going to have wet weather. If the barometer is rising, it means you're going to get a lot drier, potentially cooler air, and that means usually sunny weather. So that's why you can see they make those predictions on the barometer. It's based on the fact that the density of the air is a pretty good predictor of weather. So let's look at how we can interconvert some of these pressures on page 403. Practice exercise. I'm just going to leave these conversion factors up so you can see where I'm getting them. You could take any two and make a conversion factor out of them. Okay, so let's pretend we have 740, well, we're not pretending, it's what's in the question. Page 403, 745 torr. And they want you to convert it to kilopascals. So what's the relationship between torr? See, all these are 1 atmosphere of pressure. All these are different ways of stating the same thing, the pressure that is experienced at the surface of the Earth. So 101.325 kilopascals and 760 torr, that's the same pressure. So let's write these two numbers in such a way that torr is eliminated. So we're going to say 101.325 kilopascals per 760 torr. Torrs cancel, and the answer you get is 99.325. 1645 kilopascals. Your question only had 3 numbers in it, so your answer can't have 12. So you're going to put 99.3 as your final answer to have the right number of significant figures. The next question in that series is convert 91.5 pounds per square inch into atmospheres. Okay. So 91.5 pounds per inch squared times 1 atmosphere, see I got that here, per 14.7 pounds per square inch. That allows me to cancel those, and what we get is 6.2244898 atmospheres. You're only allowed 3 sig figs, so you're going to write 6.22 as your final answer. There it is. On practice example of page 404, they talk about manometers. Manometer is just a device for measuring pressure that uses a U-shaped, well, in the old days they had a U-shaped tube, and they would keep one end open and one end closed, and the closed end had an air bubble trapped in it that was at the same pressure as the atmosphere. And or you could vacuum out all the air if you wanted, and the manometer would work like a barometer. So nowadays when they have manometers, it's basically a gauge that senses the pressure of the atmosphere and puts it on a needle so it can tell you whether the pressure is above zero. Sometimes they have manometers that go into the vacuum range, or you can have manometers that go into pressure. And typically machinery where there is pressurized liquid or air flowing through pipes, they'll have a gauge on it to monitor the pressure so that it stays within acceptable parameters. Anyway, on page 404, it says in the practice exercise, convert a pressure of 0.975 atmospheres into pascals and kilopascals. This is following a discussion of a manometer, so you'd have to have the chapter to see that. But we can still do the question. So this is practice example on page 404. So 0.975 atmospheres times 101,325 pascals, rather, not kilopascals, per 1 atmosphere. See, both of these numbers are in this list I did here. 101,325 pascals is equal to 1 atmosphere. So you should memorize all these. Cancel atmospheres, and what you get is 98,791.875 pascals, or 9.88 times 10 to the 4 pascals. You could also say 98.8 kilopascals if you divide by 1,000. One quick fact that you might find interesting: blood pressure is measured in millimeters Hg. Normal blood pressure for men is 120/80. 120 is equal to about 2.32 pounds. 120 millimeters Hg is equal to about 2.32 pounds per square inch at systole. So when your heart pumps, it exerts a pressure of around 2.3 pounds per square inch, which is not negligible. I mean, it'll cause your blood to squirt. If you ever injure your scalp, apparently the blood can squirt a couple feet. So I've been told, because the scalp is highly perfused, a lot of arteries there. If you poke a hole in one of the arteries, every time your heart pumps, you get a squirt of blood. That's why it's always a bit of an emergency if you poke a hole in a big artery, because the blood's at a high enough pressure to cause very serious bleeding in a short period of time. That's why they talk about putting pressure whenever you have those kind of wounds to prevent you from bleeding out. On page 406, they start talking about the gas laws. Now, scientists started doing experiments on gases when they noticed that they were compressible. A guy by the name of Boyle was the first one to do some experiments on the compressibility of gases. Robert Boyle, he lived between 1627 and 1691. He discovered that, using a manometer, if you doubled the pressure on a gas, it made its volume go to half as much. So he noticed there was a proportional relationship. So that came to be known as Boyle's law, that the volume of a gas is proportional to the pressure exerted upon it. So you can write that as PV is equal to K. That's the first gas law. Pressure times volume is equal to a constant. Don't worry about it yet, and it's in the notes, so I'm not going to write it on the board. It's just going to slow me down. The next guy to do some research on that was a guy by the name of Jacques Charles. And he coined Charles' law. Charles' law states that the volume of a fixed amount of gas maintained at constant pressure is directly proportional to its absolute temperature. What does that mean? If you lower the temperature of a gas, it exerts less pressure, and it'll also lower its volume. So examples of this, practical examples of how that works. In the wintertime, if you don't check your tire pressure, and if there's a significant drop in temperature, say if in the summertime it's on an average of 25 degrees Celsius above zero, and say if you're living in a place like Alberta where the temperature easily goes down to minus 25, that's a 50-degree difference in temperature. That can have a significant effect on the hardness of your car tires. So it's a good idea to readjust the pressure in the wintertime by adding a little more air in the winter and taking out some air in the summer. Typically, car tires are inflated to about 32 pounds per square inch, which is about just a little over 2 atmospheres to be considered normal operating pressure. Truck tires operate around 5 atmospheres. 5 times 14 gives you 50 to 70. 5, 6 atmospheres even. Truck tires, because trucks obviously have to carry heavy loads. Another guy that was honored by, now I don't know if he did the research directly, but Avogadro's hypothesis states that the volume of a gas maintained at constant temperature and pressure is directly proportional to the number of moles of the gas. So the more gas, obviously the more volume. So those 3 laws were combined into one big law called the ideal gas equation. So all those things, pressure, volume, and temperature, have an effect on what a gas does. Why do gases have pressure in the first place? Why do the gases exert pressure? Well, because the molecules are moving around, colliding with each other elastically, continuously, and the amount of energy they have, the amount of kinetic energy gas molecules have, and we found this out later when they developed the kinetic molecular theory to explain everything, that the energy content of a gas is directly proportional to the temperature. The higher the temperature, the more energetically the molecules collide, and the higher the pressure exerted by the gas. The other way around, if you keep on lowering the temperature of a gas, and this is something by a guy by the name of Kelvin, that name should ring a bell, a guy by the name of Kelvin discovered that if you lower the temperature of a gas, it has less and less energy. And at some point he plotted the energy curve of several gases, and he realized they all converged to zero energy when they reached the temperature of minus 273. And what do we know about minus 273? I know some of you are saying, oh, that's absolute zero. Exactly. At absolute zero, there's no more energy. So the gas molecules stop moving, and they either turn into, just before 273, because it's virtually impossible to actually reach absolute zero, because there's always a little bit of energy leaking in from the environment. But the closer you get to 273 below zero, the closer the gases come to becoming solids, which means they have very little energy. And if you could observe a gas at absolute zero, you would notice that the atoms had stopped even wiggling. They would just stay. The crystal would have no kinetic energy, and that's the point. At absolute zero, there is no more kinetic energy. There's no more heat energy in the crystal. All the atomic motion stops. So these 4 observations were combined into one idea called the ideal gas equation. So the ideal gas equation is this. PV equals nRT, where P is the pressure exerted by the gas, V is the volume the gas occupies or is confined to, N is the number of moles of the gas, R is the gas constant, which is basically a number that, depending on which units you're using for PVR and PVN and T, you'll get different numbers, because different units obviously give you different numbers. So R is meant to make all the units work out. And T is the temperature, the absolute temperature, not Celsius temperature. Don't use Celsius, use Kelvin. It's the absolute temperature measured in Kelvin of the gas. The reason why it's important to use absolute temperature is because the energy content of a gas goes to zero when the temperature is 0 Kelvin, or absolute zero. I'm going to cut it off there. And I'd like you to watch my playlist on gas laws, which are part of this profile. You know, like hours of video. Just watch a couple videos from there. and you'll see the notes that go with this, okay? All right, see you tomorrow.